In the quiet hum of our modern world, an invisible battle rages. It's a war fought not with weapons, but with intellect and ingenuity, pushing the very limits of matter and energy. At its heart lies a prize so profound, so transformative, that it could redraw the map of human civilization, the zero-resistance Holy Grail. For decades, scientists have pursued a material that conducts electricity with perfect efficiency, no energy lost as heat. This isn't science fiction, it's the bedrock promise of a room-temperature superconductor, and its achievement would be nothing short of a global revolution. Every single electronic device, every light bulb, every data center, relies on the flow of electrons through conductors. Copper wires hum with electricity, carrying power from distant plants to our homes and businesses. But this flow is never perfect. As electrons journey through these wires, they collide with atoms, creating friction, generating heat, and inevitably, losing precious energy. This fundamental inefficiency is a bottleneck on progress, a constant drain on our resources, and a challenge that has plagued engineers since the dawn of the electrical age. To understand the allure of zero resistance, we must first grasp its opposite. Electrical resistance is a material's opposition to the flow of electric current. Imagine trying to run through a dense forest. The trees, rocks, and uneven terrain impede your progress. In an electrical conductor, these impediments are the vibrating atoms and imperfections within the material's crystal lattice. Electrons, the tiny carriers of charge, constantly bump into these obstacles, dissipating their kinetic energy as heat. The story of zero resistance truly begins in 1911, in a laboratory in Leiden, Netherlands. It was there that Dutch physicist Heike Kamerlingh-Onnes, a pioneer in cryogenics, was exploring the properties of materials at incredibly low temperatures. His team had successfully liquefied helium, achieving temperatures just a few degrees above absolute zero. As he cooled a sample of mercury, meticulously measuring its electrical resistance, he observed something astonishing, something utterly unprecedented. Onnes watched as the resistance of his mercury sample plummeted. It didn't gradually decrease, it vanished entirely. At precisely 4.2 Kelvin, just minus 268.95 degrees Celsius, the mercury offered no opposition to the flow of electricity whatsoever. It was as if the internal forest of atoms and imperfections had suddenly dissolved, leaving a frictionless highway for electrons. He had discovered superconductivity, a state of matter where electrical resistance ceases to exist. Onnes' discovery was groundbreaking, but it came with a significant caveat: the extreme cold. Maintaining temperatures just a few degrees above absolute zero requires immense energy and specialized, expensive equipment, primarily using liquid helium. This cryogenic barrier meant that while superconductors held incredible promise, their practical applications were severely limited. The dream of zero-loss power grids and frictionless machines remained largely confined to the laboratory. For decades after Onnes' discovery, the fundamental mechanism behind superconductivity remained a mystery. It wasn't until 1957 that John Bardeen, Leon Cooper, and John Schrieffer, often referred to as BCS, developed a comprehensive theory. Their breakthrough revealed that at extremely low temperatures, electrons, which normally repel each other, can form peculiar bonds. They become Cooper pairs, effectively pairing up and moving together through the material. How do these electrons, with their identical negative charges, overcome their mutual repulsion to form pairs? The key lies in the vibrations of the material's crystal lattice, known as phonons. As one electron passes through the lattice, it momentarily distorts the positively charged ions, creating a slight region of higher positive charge. A second electron, attracted to this transient positive wake, follows closely behind, effectively mediated by the lattice vibrations. It's a subtle quantum dance, orchestrated by the atomic framework itself. Once formed, these Cooper pairs behave as a single entity, a boson, rather than two individual fermions. This distinction is crucial. Unlike individual electrons that scatter and lose energy, Cooper pairs can move through the crystal lattice without resistance. They are not easily perturbed by the minor imperfections or vibrations that cause resistance in normal conductors. Their collective, coherent movement is the essence of zero electrical resistance, a macroscopic quantum phenomenon. Superconductors don't just excel at conducting electricity, they also possess a remarkable magnetic property. In 1933, Walther Meissner and Robert Oxenfeld discovered that when a superconductor is cooled below its critical temperature in the presence of a magnetic field, it actively expels all magnetic flux lines from its interior. This phenomenon, known as the Meissner effect, is what gives us the stunning visual of magnetic levitation. Picture a small magnet hovering effortlessly above a chilled superconducting disk. This isn't magic, it's the Meissner effect in action. The superconductor, having expelled the magnetic field, creates a repulsive force that perfectly balances the force of gravity, holding the magnet aloft. This incredible property isn't merely a parlor trick, it's a cornerstone for technologies like magnetic levitation trains and advanced magnetic shielding, promising entirely new modes of transport in scientific instrumentation. Zero resistance and perfect diamagnetism, these two extraordinary properties define superconductivity. They are deeply intertwined, both stemming from the quantum mechanical behavior of Cooper pairs. The ability to carry current without loss, combined with the power to manipulate magnetic fields with unprecedented precision, makes superconductors uniquely valuable. However, the requirement for extreme cold remained the Achilles heel, limiting their widespread adoption and pushing scientists to seek materials that would superconduct at warmer, more practical temperatures. For decades after Anna's discovery, the critical temperature for superconductivity barely budged. Mercury at 4.2 Kelvin, lead at 7.2 Kelvin, niobium alloys slightly higher. It seemed as though nature had set a firm, frigid limit. The scientific community yearned for a superconductor that could function at temperatures achievable with liquid nitrogen, a coolant far cheaper and more abundant than liquid helium, boiling at a relatively balmy 77 Kelvin, or minus 196 degrees Celsius. The landscape of superconductivity research was dramatically altered in 1986. Researchers working independently, but often credited to Johannes Georg Bednorz and K. Alex Muller, discovered a new class of ceramic materials, copper oxide perovskites, that exhibited superconductivity at significantly higher temperatures than ever before. These high-temperature superconductors, or HTS, shattered the perceived temperature ceiling, opening a floodgate of new research and reigniting the dream of practical applications. While HTS materials could function above liquid nitrogen temperatures, their properties were complex and often anisotropic, meaning they conducted electricity differently depending on direction. They were also brittle ceramics, difficult to form into wires or practical devices. Despite these challenges, the discovery proved that superconductivity wasn't limited to the extreme cold of liquid helium. It ignited hope that room temperature superconductivity, once deemed impossible, might actually be within reach. In the ongoing war for room temperature superconductors, scientists have explored various battlegrounds. One of the most intriguing has been the realm of extreme pressure. In recent years, a class of materials known as hydrides, compounds rich in hydrogen, have shown remarkable superconducting properties, but only when compressed to pressures millions of times greater than atmospheric pressure. These conditions replicate those found deep within gas giant planets. Under these crushing forces, hydrides like lanthanum hydride have exhibited superconductivity at record-breaking temperatures for their time, exceeding 250 Kelvin, or about minus 23 degrees Celsius. This is still far from room temperature, but it's a monumental leap from liquid helium. The challenge, of course, is that sustaining such immense pressures outside a laboratory is incredibly difficult and impractical for widespread use. Yet, these discoveries provide invaluable insights into the fundamental physics that allow superconductivity at warmer temperatures. The ultimate prize, the zero-resistance Holy Grail, remains a material that superconducts at room temperature, typically defined as around 20 to 25 degrees Celsius, or 293 to 298 Kelvin, and at ambient pressure. Such a material would eliminate the need for costly and energy-intensive cooling systems, making superconductors practical for everyday applications. The sheer elegance of perfect energy transfer, unleashed from the shackles of cryogenics, would fundamentally alter our technological landscape. The search for room temperature superconductors is not just about trial and error, it's deeply rooted in theoretical physics and computational material science. Scientists use sophisticated simulations to predict the behavior of novel materials, exploring countless combinations of elements and crystal structures. They are seeking the perfect atomic arrangement, the ideal electron-phonon coupling, or perhaps even an entirely new mechanism that enables Cooper pairing without the need for extreme cold or pressure. Universities, national laboratories, and private companies around the world are locked in a fierce, often collaborative, but always competitive race. Teams of physicists, chemists, and material scientists dedicate their careers to this quest. Each incremental improvement in critical temperature, each new understanding of a material's behavior, brings them closer to the ultimate prize. The competition is intense, driven by the profound implications of success and the prestige that awaits the discoverer. Perhaps the most immediate and impactful revolution brought by room temperature superconductors would be to our global power grids. Currently, vast amounts of electricity are lost as heat during transmission over long distances. Imagine a world where power lines conduct electricity with absolute zero loss, delivering every electron generated directly to its destination. This would fundamentally transform energy efficiency on a planetary scale. Estimates suggest that global electrical grids lose approximately 8 to 15% of all generated electricity due to resistance. While this varies by region and infrastructure, it represents a staggering amount of wasted energy, billions of dollars and vast quantities of resources literally vanishing into thin air as heat. Room temperature superconductors could reclaim this lost power, making our existing energy production significantly more efficient and reducing the need for new power plants. Beyond efficiency, zero-resistance power lines would enable entirely new energy architectures. We could efficiently transmit renewable energy from remote solar farms or offshore wind parks to distant population centers without significant degradation. Energy storage could also be revolutionized, using superconducting magnetic energy storage (SMES) systems that hold charge indefinitely with no losses, offering unprecedented grid stability and resilience. Imagine travel at speeds rivaling aircraft, but on the ground, quiet and vibration-free. Room temperature superconductors would unleash the full potential of magnetic levitation, or maglev, transport. Current maglev systems use powerful electromagnets, but they still face challenges related to energy consumption and cooling. A room temperature superconductor would provide perfect levitation and propulsion with minimal energy input, making maglev trains the ultimate mode of high-speed, efficient surface travel. Traditional trains suffer from friction between wheels and rails, limiting speed and increasing wear. Maglev, by eliminating physical contact, removes this friction entirely. With room temperature superconductors, the cost and complexity of cooling could be removed, enabling broader adoption. Passengers would experience unprecedented smoothness, and maintenance costs would plummet due to the lack of moving parts. It's a fundamental paradigm shift in how we move people and goods. Beyond energy and transport, the advent of room temperature superconductors would profoundly accelerate the quantum computing revolution. Many leading quantum computing architectures, particularly those based on superconducting qubits, require extremely low temperatures, often millikelvin ranges, to maintain their delicate quantum states. This cryogenic overhead is a major hurdle in scaling quantum computers to practical sizes and widespread use. Room temperature superconductors would allow superconducting qubits to operate without the need for massive, expensive dilution refrigerators. This would dramatically simplify design, reduce operational costs, and enable the creation of more robust and scalable quantum processors. Such a breakthrough could unlock quantum computing's full potential, allowing us to tackle problems currently impossible for even the most powerful classical supercomputers, from drug discovery to materials design and complex AI. The quest for unlimited, clean energy culminates in nuclear fusion, the process that powers the sun. Harnessing fusion on Earth requires containing superheated plasma, hotter than the sun's core, in powerful magnetic fields. Superconducting magnets are essential for achieving this, but their cryogenic requirements add immense complexity and cost to experimental fusion reactors like ITER. Room temperature superconductors would revolutionize fusion power, making it far more achievable and economically viable. With room temperature superconductors, fusion reactors could employ far stronger and more efficient magnets, allowing for smaller, more cost-effective designs. This would dramatically reduce the engineering challenges and the sheer scale of current fusion projects, bringing the dream of abundant, clean energy closer to reality. Imagine a world powered by miniature suns, safely contained and offering limitless energy with minimal waste. This is the profound promise of RTS in fusion. The impact of room temperature superconductors extends far beyond power grids, transport, and quantum computing. Medical imaging, for instance, relies heavily on superconducting magnets in MRI machines. Currently, these require constant cooling with liquid helium, a finite resource. RTS would make MRI cheaper, more accessible, and even portable, transforming diagnostics globally. Furthermore, advanced scientific instruments, particle accelerators, and sensitive detectors would all see unprecedented advancements. The elimination of cryogenic cooling would also enable radical miniaturization. Superconducting circuits could be integrated into everyday electronics, creating devices with unimaginable speed and efficiency. Think of microchips that generate no heat, or sensors with unparalleled sensitivity. From personal electronics to advanced robotics and space exploration, the ability to build superconducting components that operate at ambient temperatures would unleash a torrent of innovation, creating entirely new industries and capabilities. Despite the tantalizing promise, the war for room temperature superconductors is far from over. The materials discovered so far, whether needing extreme cold or extreme pressure, have illuminated pathways but not yet yielded the ultimate prize. The challenge lies in finding a material that combines the complex quantum mechanics of Cooper pairing with the robust structural stability needed to function reliably at everyday temperatures and pressures. The history of science is often a blend of meticulous calculation and serendipitous discovery. The next room temperature superconductor could emerge from a sophisticated theoretical model, guiding scientists to synthesize a specific, never-before-seen compound. Or it could be stumbled upon accidentally, a strange anomaly in a routine experiment, much like Anna's initial discovery. The scientific method embraces both pathways, patiently probing the universe's secrets. The true Holy Grail is not just a room temperature superconductor, but one that is also practical and scalable. It must be manufacturable at reasonable cost, durable, and easily formed into useful shapes like wires or thin films. The material science aspect of this quest is as critical as the pure physics. Researchers are exploring exotic compounds, intricate crystal structures, and entirely new ways to induce the Cooper pairing phenomenon. If a viable room temperature superconductor is discovered, its implications will be so profound that ethical considerations and global access will become paramount. How will this revolutionary technology be shared? Will it exacerbate existing inequalities, or will it be a force for global equity, bringing affordable energy and advanced technology to every corner of the world? These are questions that humanity will grapple with long before the material itself is perfected. Despite the formidable challenges, the scientific community remains driven by an unwavering belief in the possibility of the zero-resistance Holy Grail. The vision of a world transformed, boundless, clean energy, instantaneous, silent travel, and computing power beyond imagination, fuels countless hours of research, experiment, and theoretical exploration. It's a testament to human curiosity and our relentless pursuit of a better future. The war for room temperature superconductors is not a finite conflict with a clear end date. It is an ongoing frontier of discovery, a testament to the human spirit's desire to push boundaries and unlock nature's deepest secrets. Every failed experiment, every incremental success, contributes to a growing body of knowledge that will one day, inevitably, lead to the ultimate breakthrough. When that day arrives, the world as we know it will be irrevocably changed. The moment a stable, ambient pressure, room temperature superconductor is demonstrated, it will echo Heike Kamerlingh-Onnes's 1911 discovery, but with exponentially greater impact. It won't just be a scientific curiosity, it will be a cornerstone of a new technological epoch. From the smallest microchip to the largest power plant, its influence will be pervasive, redefining our relationship with energy, technology, and the very fabric of modern life. Imagine a silent revolution. No more wasted heat from electrical components, no more humming transformers, no more friction in transport. The world would become quieter, cleaner, and vastly more efficient. This profound shift, driven by the elusive physics of perfect electron flow and magnetic expulsion, would touch every aspect of our existence. It's a vision that continues to inspire, a dream that fuels the relentless pursuit of the zero-resistance Holy Grail. The true extent of the changes brought about by room-temperature superconductors might even exceed our current imagination. Just as early pioneers of electricity could not foresee the internet or global satellite communication, we may only be scratching the surface of what zero resistance could unlock. This isn't just about optimizing existing technologies, it's about enabling entirely new ones, reshaping industries, and expanding the very boundaries of human potential. The story of superconductors is one of persistence, of scientists undeterred by extreme conditions, theoretical puzzles, and the sheer difficulty of manipulating matter at its most fundamental levels. From the freezing depths of liquid helium to the crushing pressures of hydride synthesis, each step has brought us closer. The journey exemplifies the scientific endeavor, a continuous push against the unknown, driven by curiosity and the promise of profound impact. As research continues, as new materials are synthesized and new theories are tested, the horizon of room temperature superconductivity beckons ever closer. It remains a pinnacle of modern physics and material science, a challenge that embodies the ambition and ingenuity of humanity. The war for the zero-resistance Holy Grail may be long and arduous, but the potential rewards are immeasurable, promising a future that is truly electrified, truly transformed, and truly unlimited. Beyond the initial discovery, a room temperature superconductor would face another gauntlet: scalability. Can it be produced in industrial quantities? Will its properties remain stable outside of pristine laboratory conditions? These are the questions that will define its true impact. The path from a lab bench marvel to a global infrastructure revolution is paved with engineering hurdles, material science innovations, and economic realities that must all be overcome. Interestingly, superconductivity's properties are often compared to a perfect vacuum, where there's nothing to impede motion. While a vacuum is empty space, a superconductor is a highly ordered material that creates an electrical vacuum for electrons. This analogy helps convey the profound nature of zero resistance. It's not just a little bit better, it's fundamentally different, eliminating a barrier that defines all conventional electrical flow. At the heart of the challenge is understanding how to engineer material structures at the atomic level. The precise arrangement of atoms, the distances between them, and the types of bonds formed all influence electron behavior. This calls for incredibly advanced techniques in synthesis and characterization, using tools like X-ray diffraction, electron microscopy, and spectroscopy to peer into the very architecture of potential superconducting compounds. Theoretical physicists play a crucial role, developing new models and refining existing ones to explain observed superconductivity and predict new phenomena. They explore exotic quantum states, topological properties, and the interplay between electrons and lattice vibrations under various conditions. Their insights guide experimentalists, narrowing down the vast chemical space of potential materials and offering new conceptual frameworks for achieving the elusive goal. Modern computational power is an indispensable ally in this pursuit. Supercomputers can simulate the quantum behavior of electrons in complex materials, predicting properties like critical temperature and stability before a single atom is synthesized in the lab. This materials-by-design approach drastically accelerates discovery, sifting through millions of hypothetical compounds to identify the most promising candidates, transforming a needle-in-a-haystack search into a more targeted expedition. Even with significant progress in achieving higher critical temperatures, the fundamental why of high-temperature superconductivity is not fully understood. While the BCS theory explains conventional low-temperature superconductivity, a complete theoretical framework for HTS materials remains a subject of intense research and debate. Unraveling this mystery could provide crucial clues for designing the ultimate room-temperature superconductor. Some researchers speculate that Cooper pairing in high-temperature and potential room-temperature superconductors might involve mechanisms beyond simple electron-phonon interactions. Exotic excitations, magnetic fluctuations, or even purely electronic interactions could play a role. Exploring these alternative pairing mechanisms is a vital part of the quest, potentially revealing entirely new pathways to zero resistance that bypass the cryogenic constraints of conventional materials. In conventional conductors, impurities and defects are detrimental, increasing resistance. In superconductors, however, their role can be surprisingly complex. Sometimes, specific types of doping or engineered defects can actually enhance superconducting properties, stabilizing Cooper pairs or increasing the critical temperature. Understanding this intricate relationship between material perfection and imperfection is another key to unlocking the zero-resistance Holy Grail. This monumental challenge requires a truly multidisciplinary effort. It draws upon condensed matter physics, quantum mechanics, inorganic chemistry, material engineering, and computational science. Experts from diverse fields collaborate, bringing unique perspectives and tools to bear on the problem. This convergence of disciplines is a hallmark of modern scientific progress, where the biggest breakthroughs often happen at the interfaces between traditional boundaries. Superconductors can carry enormous current densities compared to normal conductors without overheating. A room-temperature superconductor could mean vastly more compact and powerful electrical components. Motors could be smaller and more efficient, power transformers could shrink dramatically, and even electrical generation could become more densely packed. This energy density revolution would enable sleek new designs and capabilities across countless industries. The journey from theoretical prediction to a working, stable material is long and often fraught with setbacks. Many promising theoretical compounds never materialize in the lab, or if they do, their real-world properties fall short of predictions. The experimental verification is rigorous, requiring precision measurements in challenging environments. This gap between theory and reality is where much of the war for room-temperature superconductors is currently being fought. The discovery of a room-temperature superconductor would undoubtedly usher in a new chapter in condensed matter physics. It would force a re-evaluation of our understanding of electron interactions, quantum mechanics at macroscopic scales, and the very nature of matter. This profound intellectual reward, the deeper insight into the universe's fundamental laws, is as significant a motivator as the technological applications themselves. Superconducting magnets are already the strongest man-made magnets, essential for applications like MRI, particle accelerators, and fusion research. With room-temperature superconductors, these magnets could become even more powerful, compact, and energy-efficient. Imagine building a new generation of particle accelerators in urban areas, or vastly more powerful MRI machines that reveal biological details currently unimaginable. The magnetic frontier would be pushed to its absolute limits. For nations around the world, the promise of room-temperature superconductors extends to energy security and independence. With ultra-efficient power grids, countries could more effectively harness indigenous renewable energy sources, reducing reliance on imported fossil fuels and volatile international markets. This would not only have economic benefits but also geopolitical ramifications, reshaping. The pursuit of the zero-resistance Holy Grail is more than a scientific challenge, it's a testament to humanity's aspirational spirit. It embodies our desire to overcome fundamental limitations, to engineer a better future, and to harness the deepest secrets of the universe for the benefit of all. The war for room-temperature superconductors is a war for a future without limits, a future that is cleaner, faster, smarter, and infinitely more powerful.